Good morning, everyone. So this is the third lecture of the webinar series which was conducted. So the previous two sessions which were held earlier, one was MIDAS Civil, the introduction of MIDAS Civil. The second was conducted on the curved box girder bridges. So both of the sessions have been conducted and the video link has been shared with you all. So today we will be looking at the pre-stress skewed girder bridge and how to design that in MIDAS Civil. So once we have finished the session, we will share you the link to the session. And if you have any questions, so you can type them in the message window, chat window. If possible, I will be answering them in between the session, or else I will take all the questions at the end of the session. Okay, so we will be starting with the topic for today, which is skewed pre-stress girder bridge. We will see how to model them in MIDAS Civil, and after that we will see how the design works in MIDAS Civil. Okay, so I will just move to my presentation. So hi everyone, I am Anuj Asati. So I am working with MIDAS Civil from past 1 year, and I am based at Navi Mumbai office in India. So today we will be looking at skewed pre-stressed two-span girder bridge. So first of all, we'll be looking at the introduction to skewed pre-stressed girder bridge. Then we'll see the modeling methodologies which can be used to model the bridge in MIDAS Civil. Then we'll see the moving load application as per ASTRO LRFT moving load cases. And then we will see the design of pre-stressed girders as per ASTRO LRFT and for our substructure here. Okay, so moving on. So today we will be covering a two-span, 23-meter span each I-girder bridge. The skew angle for our bridge is 30 degrees. So it is a simply supported composite bridge consisting of 5 precast post-tension girders which are equally spaced at 3 meters. And it is a PSC beam, so there will be pre-stressing. It is a post-tension pre-stress girder. Okay, so today what we are going to see is how to generate a composite section in MIDAS Civil. Then how to use pre-stressed composite bridge visual. So it is a very powerful tool using which we can generate any type of pre-stressed composite girder bridge, be it in a skew, be it in curvature. So all these things we are going to cover today. After that, we will see how to apply moving load in a skew bridge as per ASTRO LRFT. Then once we have done all these things, then we will move on to results. So how to interpret tendon losses, how to interpret forces and stresses in girder. Then we will see the girder design, pier design in MIDAS Civil. Okay, so now we will be starting with the modeling part. So basically this is the geometry of our bridge. So it is a two-span PSC girder bridge. So we have, if you can see here, we have 5 girders, each equally spaced at 3 meters. And it is a 23-meter span each. And the skew angle is 30 degrees. The width of my total deck is 15 meters. And my carriageway width is around 14 meters. Okay. And the moving load, as I mentioned earlier, we are going to apply it as per ASTRO LRFT. And the time-dependent material properties we will be giving as per CEB FIP 2010 code. Okay. So the general details of my girder bridge I am going to share now. So the depth of my deck slab will be 0.25 meters. And the deck and the other dimensions are mentioned as in the figure. So the structural, the configuration for my bridge is the expansion joint between two spans will be of 40 mm, and as I mentioned earlier, the girders are spaced at 3 meters center to center, and the total span is 23 meters. So this is how my the span of my bridge will look like. Okay, so now I will take you to the software, and we will see how we can generate, how we can model this type of bridge in MIDAS Civil. Okay, so I will open the So this is my main MIDAS Civil window. So I hope you have attended the session first and second earlier, so you may be knowing all the different sections of the software. So how what is this tree menu here does, what this tree menu 2 does, what this message window and this main menu does. So for some people who have joined only in today's session, so I will just give a brief introduction of the software. So basically this is my main window of my software. So here whatever modeling I will be doing will be reflected in this main window. What we see here at the top is my main modeling window. So sorry, it is my main menu. So using this menu, I will be creating my model. So basically, if you go to this view tab, so here there are various view options which are available for us. So while modeling, we will be requiring different views of my structure. So to assign the properties and to perform different operations on my structure. So all these views are based on a CAD software. If you're aware of any CAD software, all the views which are available there are available in our software as well. Then the main feature of MIDAS Civil is this structure tab. So in this structure tab, we have the wizards. So what wizard does is it reduces the modeling effort of an engineer. So any type of bridge you want to model, you can model using this wizard options. So we have all type of wizards here. So basically, if you want to model a simple arch, frame, truss, you can use this base structure wizard. If you want to model, suppose a suspension bridge, so we can model it using the suspension bridge wizards. So we need to know the geometry of my bridge. So based on the geometry, I just need to input all the parameters of my bridge and generate the section. So today we will be using this Prestressed composite girder wizard. So once I will go in detail once we start the modeling. So after that, here we have this node and element tab. So basically once your structure is generated using any of the wizard, we can edit or modify our structure using these options which are available here. So keeping in mind any of the CAD software, what are operations we can do in a CAD software can be done in MIDAS Civil, be it translate, extrude, divide, merge, intersect. So all these operations can be performed in MIDAS Civil. Similarly, if the properties, section properties, material properties can be defined here, then coming to boundaries, so boundaries of your bridge, be it spring type or support type can be defined using this boundary tab. Then we move on to load tab. So whatever loads which are coming on the bridge will be defined in the load tab. Similarly, analysis. So whatever type of analysis we are performing here can be done in this analysis tab. Then once we have performed the analysis, we will move on to result. So we can view all the types of results which we require from this result tab. Then we move to design. So we have a dedicated section for PSC design. So we will be looking this in detail for our PSC box girder, PSC eye girder bridge. So we will be designing our PSC girder using this PSC tab. Then if pushover, design, rating, query, and this tools. So if you notice one thing, so if you see this, our main ribbon menu is designed as per the workflow of an engineer. So as we start from modeling, we assign the property, we assign the boundary, load, analysis and other things as it goes on. So as the process of an engineer goes, these tab has been designed. So I hope you are aware of all the options. So we will start our modeling for today's session. So how we are going to model is, first what we are going to do is, first we are going to define the material properties for my bridge. Then after that, what I will be going to do is going to define the sections. So sections of my girder, sections of my pier, sections of my pier cap. So I'll be designing all those sections, and after that we will move on to my wizard, Prestressed girder, composite girder wizard, and there we'll move on to modeling. So first thing which I need to do is I need to go to properties and I need to define my material properties. Okay, so we go to properties, we go to material properties, then this new window will open up. Then here I will press add. So I just need to define my material properties. So first property which I am going to define is for my girder. So my girder is a concrete material will be defined for that. So I will select the standard for which I need to define. Okay, so for that I will just select ASTM RC and I will select the grade. So for this grade I am selecting grade C5000 for my girders. Okay, once I have selected from the drop down of database, you can see the properties of my concrete has been updated here. Once I press OK, my property of my girder has been added. Similarly, I need to add a property for my slab. So again I will go to concrete, type of design I will select as concrete, standard I will select as ASTM RC, and from the drop down I will select grade C4000 for my slab. Okay, as you can see the properties of my material has been updated here. I will just press OK. So now you can see both the concrete materials are added for my slab and for my girder. So whatever property which I am using for my slab, same property I will be using for my substructure as well. So now I need to define a property for my tendon. So for that tendons I need to define the property. So it will be type of design will be steel. I will select the code as ASTM steel, and from the database I will select A53 material. Okay, so once I have entered, the properties will be updated here in the steel sections, and I will press OK. So now all the properties, material properties which I will be using in my structure I have defined. Okay, so now there is this time dependent material sections if you see here. So the purpose of this time dependent material section is to incorporate the effects of creep shrinkage in my bridge. So basically how I'm going to do this analysis is I'm going to model my bridge, I'm going to define the construction stages, and then based on the construction stage and the age of my bridge I am going to find out the time dependent effects due to creep shrinkage in my bridge. So for that I need to define these time dependent material properties. Okay, so first I need to define, first I will change my units back to Newton mm, and I will click on this creep shrinkage option. I'll click on add. So now I will select code as CEB-FIB. So first time dependent creep and shrinkage property I will define for my girder material, which is C5000. Okay, so the characteristic strength for my girder is 34.474 Newton per mm square. Relative humidity I will keep it as 70. So now the notional size. So notional size is the parameter which governs the shrinkage and creep. So basically the rate at which shrinkage will happen, it is governed by this notional size. So this will depend on the surface area and parameter and perimeter of my section, whatever section I'm going to define. So as of now, I will give it a size of 1000 mm. But once I have defined my section, I can update it later based on my section. So for now, I have defined it as 1000 mm. And the type of cement I am taking 32.5 R and 42.5 N. And the age of concrete for beginning of shrinkage, I am keeping it as 3. I will just press add show results. So you can see here, so these are the creep coefficient based on the age of my concrete. So you can see here, these are the age in days, and this is the value of my creep coefficient. Similarly, this is the value for my shrinkage strain based on the age of the concrete. Okay, so once I have defined this for my girder, similarly I need to define for my deck. So for deck, the material property is C4000. The compressive strength for my C4000 will be 27.57 92 MPa. Similarly, I will give the notional size as 1000 mm for now. Similarly, all the parameters I am keeping same. You can see the creep coefficient and shrinkage strain are generated here. I'll just press OK. Okay. Similarly, I need to define the time-dependent material property for my concrete, compressive strength of concrete. So I will just name it as C5000, and I will select CPFIP 2010. So now mean compressive strength of concrete at 28 days. So that will be my characteristic strength plus standard deviation in my standard deviation of my material, concrete material. So as of now, I don't know the standard deviation. So I will take it as 40 MPa for C5000, and the cement grade was, so based on whatever your standard deviation and FCK, you need to calculate the mean compressive strength and give that value here. Okay, so I will just redraw the graph. So this is how my compressive strength is going to change as per the age of my concrete. Okay, so I will just press OK here. Similarly, I need to define for my deck material C4000. Again, I will select CPFIP, and I will take the mean compressive strength as 30 MPa. Okay, just update the graph, press OK. So once I have defined the creep shrinkage and compressive strength time dependent material property, I need to link it to my original material property which I have defined here. Okay, so to link that, we need to we will use this material link. So here I need to select my creep and shrinkage material property, and I need to link it to my original material, grade C5000. Okay, once I have just press add, so that property will be linked to my material. Similarly for C4000, okay, so I have linked both the properties to my material. Okay, so till now what we have done is we have defined the material property, we have defined the time dependent material property, and we have linked time dependent material property to my material property. So now the next step is to define my section. Okay, so for that I need to go in properties, there is this section properties icon. So once I click that, this new window will open. So once I press add, so you can see here this tab will open, section data tab. So here there are various types of section which I can define here. So one is this DB database user type of section. So here from a vast type of sections, I can select any of the section and we can define that. Okay, and there are this according to a database of different codes, some various sections are available. So I can use that, or I can give a user defined section as well. Similarly, there is this value type SRC, combined, PSC, tapered, composite, and steel girder section. So you can explore all the different types of section which we can define in MIDAS level. For today, we are going to define using composite sections. Okay, so I'm going to define a composite section. I'll just name it as Girder 1. Okay, I will select it as composite I. Okay, I will just switch on the symmetry tab. Okay, so I forgot to change my units here. So I'll just change the units first, so it will be easier for me to define the section. I'll change that to kilonewton meter. I'll go to add, composite, girder 1. Okay, the type of section will be composite I. Symmetry on. Width I will keep it as 3, as the effective spacing for my girder to girder is 3. Thickness of my slab will be 0.25 meters, and this HH I will keep it as 0. So I need to enter all these values here. So HL1 will be 0.15. So based on your requirement, you can define the section. So I am using, I have already defined a section which I am using a standard section from a project, already used project. So this will be 0.1, 1.2, .1, HL 5.25, BL 1.15, BL 2.5, and BL 4.45. So you can see whatever properties I have entered here, whatever dimensions I have entered here, based on that my section has been created here. So you can see this is my 3 meter width of my slab, 0.25 thickness, and based on my I girder, whatever properties I have entered here, the section has been created. Okay, so once I have created this section, now I have to select the material properties for my section. So basically when I am defining this material property here, so what it is going to do is, yeah, just a second. Yeah, so based on whatever material property I have defined here, it will calculate the section parameters. So basically the section properties of my section are going to be calculated based on whatever properties of material I am defining here. So just I will, so for girder I have selected C4000, sorry, C5000 for girder. Girder to C5000. Okay, so based on that, it will calculate the E ratio the temperature coefficient ratio, and based on this, the section properties will be calculated. Okay, based on whatever material property I have defined here. Basically, the software will convert this into a transform section, and to convert it into transform section, we need this material properties. So based on that, it will calculate the composite section properties. Okay, so once I have defined these things, I need to change the offset. So basically, we are going for center top modeling. So I will just change the section to center, just change the offset to center top. So once I have entered all these things, I just need to press OK. So this is how I have defined the composite section in MIDAS Civil. Okay, similarly, I need to define my diaphragm section. So for defining diaphragm section, I am going to use a solid rectangle. So this I will name it as end diaphragm. Okay, and I will be using user type section. So height I will be using it as 1.4 and depth as 0.45. Now again I have to change the offset to center top. But here what I will do, here I need to give it an offset of minus 0.25. This is because my deck slab thickness is 0.25 and I want my diaphragm below my deck section. So for that I need to give an offset of minus 0.25. Okay. Similarly for intermediate diaphragm, solid rectangle. Point 3 section. Again the offset is center top. Again I will give it as minus 0.25 from extreme fiber. Okay. Okay, once I have defined these sections, now I need to define my pier cap section. So to define my pier cap section, again I will select solid rectangle and user type. The section for my pier cap is 1.5 cross 1.5 and offset again it is at center top. Okay, so now I need to define my pier section. My pier section is a solid track section. So it is a user type. Height is 1.5 and width is 3 meters. So this is my pier section. Okay, for this offset will be center. Okay. So now we are done with material properties, time-dependent material properties, and section definition. Okay, so if you see in the work menu, so whatever we have done till now will be updated in the work menu. So first we have defined the material properties, which are updated here. Then we define the time-dependent material properties for creep and shrinkage and for compressive strength. Both the properties have been updated here. And this is the material link which we have given between our material and time-dependent material. Then the sections which we have defined. So girder, end diaphragm, intermediate diaphragm, pier cap, and pier. So now now our point is to model our bridge. So there are two ways to model. One is by going first we create the nodes, and from the nodes we create the elements like the standard procedure which we follow. And the other option, so this is a skew bridge, so it will be difficult for us to create using the normal standard procedure by creating nodes and elements. As the bridge is in skew, so to copy all the members we need all the we need the distances for the skew angle and all those things. And with that, I need to give my beta angle to all the boundary conditions which I am going to apply. So so what beta angle is, we will be looking into it after some time. So the easier option is to model it using the wizard. So for that, we are going to use PSC Composite Bridge Wizard. So if you open this wizard, it will look something like this. So there are 5 tabs here. So first is my layout tab. So basically here what I am going to give is what is the layout for my bridge. So based on what is my span information, support skew angle, what is my deck width, what is the spacing of my, so basically what is the spacing between the girders, what is the spacing of end of girder to my support, and what is my substructure dimensions. So basically the layout of my bridge I am going to specify here. Then when I move on, this is the section tab. So basically I will define all the sections of my bridge. So basically what is my girder section, what is my diaphragm section, and what is how, suppose if you have given different sections along your single span, so how your each span, how the sections are going to be changed, so that you're going to specify here. And then your girder offset, so from center line, how your different girders are placed along the transverse direction. So in our case it is at 3 meters spacing each, so that we need to define here. Okay, then we move on to tendons. So basically you can give your tendon profile, so how you have defined your tendon profile for your girder, we are going to specify that here. Okay, so after that, what are the loads which are going to be applied on my bridge? I'm going to specify that. So what you see here is my lane definition. So basically how my bridge definition is there. So I need to give it here. And what are the loads which I want to be considered here? I need to specify that. Then once I have done that, I need to specify the construction stages and the duration of the construction stages, and my structure will be generated. Okay, so we will start one by one each tab. So first is my layout. So for that, so ours is a 23 meter span deck. So I will just enter my span configuration. So two spans at the two spans of 23.02 meters each, and my deck width, total deck width is 15 meters. Okay, and the support skew angle, so my support skew angle is 30 degree as mentioned earlier. Okay, so now as we have seen in the bridge layout, the expansion joint, the spacing between two decks was 40 mm. So I will just give 40 mm spacing here, and the distance between the edge of my deck and to that of my support, it is 0.5 meters. Okay, so now we don't have any curvature as of now, but if you have curvature, then we can define the curvature for our bridge based on the radius, and if it is convex or concave. Okay, so here you can define either my girders are at same spacing or same skew angle. So do I want my girders parallel to each other, or do I want them to have same skew angle? So based on that I can define my curvature. Okay, and now do I want to model substructure or not? So if I don't want to model substructure, so what I can do is I can give the stiffness of my abutment and pier, and it will create a point support spring with the equivalent stiffness. But if I want to create the substructure, so I need to define everything here. So what is the elastic link? So how I want to connect my superstructure to my substructure. So with elastic link, so I need to give the stiffness of the elastic link here. Okay, so this is the how the connection is going to happen. So this is my deck slab, and this is my girder, and my girder is placed on my pier cap, and it is connected via rigid elastic links. So these elastic links represent the bearings. So these elastic link will have the stiffness of my bearing. Suppose I have provided an elastomeric bearing. So based on the shear rating of my elastomeric bearing, the stiffness of longitudinal stiffness will be calculated, and that stiffness will be provided for my bearing in this elastic link. Okay, so we are going to model the substructure as well. So what I am going to do, so Kx is the local x direction of the spring. So when I am going to assign that, it is going to come in global z direction. So in that direction, the stiffness is going to be very high. So I have just assigned 1 e to the power 8 stiffness. And the other two directions, I am giving it 1000 stiffness. Okay. Similarly, here I will give 1000. Okay, and elastic link depth I am keeping it as 0.1 meter. Now coming to so for pier, I want to model the pier with C400 grade of concrete, and the section is the pier section which we have already defined. Okay, length I will keep it as 13.5 meter. So this is the pier cap, this is the pier cap section. So the length of the pier cap I am keeping it as 13.5 meter. So for column, I will select pier section. Height I will keep it as 10 meter. There is no need for spacing as we have only 2 spans. And for pier, we are keeping it as fixed at the bottom. Okay, so this is the layout for my bridge. So once I am done with that, I will move on to sections. Okay, so here the deck thickness we have kept it as 0.25 meter. Okay, so material for my deck is C4000, material for my girder is C5000, and for diaphragm as well I am keeping it as C5000. Okay, so end support I am giving it as end diaphragm, which we have already defined. Okay, at pier also it will be as end of my first span, so that will also be as an end diaphragm. Intermediate, we are going to provide intermediate diaphragms. Okay, Then coming to this, so number of girders for us, we have 5. So I will just update it. So here I have 5 girders. So each is spaced at 3 meters spacing. So this will be at 6 meter. This will be at 3 meter. This will be spaced at 0 meter. Three, 6. Basically, this is -6, -3. Okay, so this is how my girders are spaced. So now coming to transverse deck element. So basically what we are going to do, so how I want to create my transverse deck element. So there are 3 options. Either I can give total divisions, I can give distance between the transverse elements, or I can give divisions per span. So basically I am going to give divisions per span. So each span is around 23 meters. So I want to divide my span in 21 parts. So it is each part is around little bit more than 1 meter. Okay, so the less spacing of your transverse deck element, the better will be the distribution of loads among your girder. So basically whatever load we are going to apply, that load is going to be transferred to my girder using these transfers. So the distribution is going to happen via these transverse deck elements. Okay, so now my bridge is in skew. So rather than going for a perpendicular angle type, I will go with skew angle. Okay, so now suppose you had different sections. So suppose now we have defined only a single section for my girder. So but if you had a different section at support and different section at mid part, so that type of profile can also be generated. So in that case, so from starting to whatever point we have the support section, just we need to give that value here and select the support section. Similarly, I need to give the full configuration for a single deck. Similarly, I need to create for span 2 as well. Okay, so as of now we have only one girder, so that's why full girder, the full span will have the same girder, same section for the full girder. Okay, and as per ASHTO, we need to get the stresses at each 10th point. So at span by 10, each span by 10 location, I need the forces stresses for my bridge. So for that option, we have this generate 10-point element. So when we check on this option, so an element will be created at each span by 10th location. Okay, as of now we don't need that, so I am going to switch that off, or else the number of elements will increase. So I have done, once we have defined my section data, I will move on to my tendon data. So now I need to define the tendons. So based on the type of tendon which we are providing, is it hard or is it curved? So based on whatever H2, H3, L1, D, all these values, we need to create my tendon profile. So for now, for this bridge, what we have here is a curved profile. So first we need to create a tendon property. Okay, so tendon property is nothing but what kind of tendon we are going to provide. So I'll just give the name tendon. Then it is the type of pre-stressing we are going to do. So it is pre-tension, post-tension, or is it an external tendon that we need to select from here. So for now we are doing a post-tension beam. So I will select a post-tension element. Now I need to select the material. then the total tendon area 15.2. I'm going to have 12 strands. Okay, and the duct diameter I will keep it as 90 mm, so 0.09, and this relaxation coefficient will be calculated as per CP/FIP. Okay, so ultimate strength and these things I have kept as it is, or else based on your tendon you need to provide your ultimate strength and yield strength. And the curvature factor, friction wobble, wobble friction factor we need to provide here, and the anchorage slip, what anchorage slip is allowable for our beam we need to specify here. We need to specify the type as well, is it bonded type or unbonded type. So once we have done, so for our case it is bonded type, so I will just press OK. So this tendon profile has been defined. Okay. So once I have defined the tendon profile, now I need to give, so the type of tendon which I want to provide. So I need to provide curved tendon. Okay, tendon property I will select from the drop down. Number of tendon I will keep it as 1. So the value of this H1 is at the end of the section, how much is the H1. So in our case it is for first tendon it is 0.5. H2 is this value. So this is 0.57. Okay, so this is how my first tendon will be created. Similarly, I will create the tendon 2. Number of tendons will be 1. This is 0.9, 0.35. These two tendons are created. Similarly, I will create the third tendon. This is 1.3, 0.13. So this is how the 3 tendons have been created for my span. Okay, so I need to provide the jacking stress here. So the jacking stress will be 1395, which I have considered for my bridge is 1395, and I want the grouting to be done after 1 day. First one stage. Okay, once I have assigned this, I will just press add. So these 3 tendons which I have defined here are assigned to my span 1. Similarly, I need to assign the same tendon profile to my span 2 as well. So again I will press add. So this tendon profile has been created for both the spans. Okay, so once you can see where my tendons are created. So this is at 1.3 meters, this is at 0.9 meters, this is at 0.5 meters. Okay, so total depth of my girder is 1.8 meter. Okay, so once I have defined my tendons, I will move on to load. Okay, so here this is the total, so my total deck width is 15 meters. So I want my carriageway width to be 14 meters. So for that my B1 is 0.5, my B2 is 7 meters, B3 we have kept it 0, and this is also 7 meters, and this is 0.5 meters. So you can see my total deck width is 15 meters. Okay, now moving on, the dead loads. So I want the dead loads equally be applied to all the girders. For this is the dead component that is fine. Then DC, after composite. So after composite, whatever loads are going to come on my deck, that are barrier load, median strip and additional load. So I want my barrier load to be applied at the edge of my bridge, where the barrier is going to be casted. So I will not check on this option. If I check this option, whatever loads I have assigned here will be equally divided to all girders. Okay. Similarly, for bearing course, bearing surface, do I want this equally applied to all? So for this I want, yes, I want to be applied. So I will select, check on this option. Okay. The weight density for my concrete is 25. The thickness is 0.25 as discussed earlier. So for barrier, I will keep it as 9 kilonewton per meter, and we are not going to model this median strip, so I will check off this option. Here I will give this as 22 kilonewton per meter, weight in per meter cube, and the thickness of my bearing course I will keep it as 0.1. Okay, so moving load we are not going to define here. We are going to define it post we have generated the section using Wizard. Okay, so now we will move on to construction stages. So now here, before discussing the construction stage, what we are going to do is first I am going to define the reinforcement for my section. Okay, so for that I will go to define reinforcement. So it will open a new tab for us to define the reinforcement. So for defining the reinforcement, I will select the section. So this is my girder section with slab and the eye girder. So there are various ways to add the reinforcement here. So either I can define points, I can define line, arc, circle, polyline, and there is this multi-add option as well. So we are going to use this multi-add option. So once I click on this multi-add option, so what it will ask me is, so there are various methods as I told you. So we are going to go with line input method, type A. Okay, we'll select this reference as centroid. Okay, so this is the reference in Z direction. So either this can be top or bottom. So we are creating the reinforcement from top reference. Okay, so Y is 0. So Z is 0.06. So that means I am considering a cover of 60 mm from the top. And the number of bars which I want to create here is 20. Okay, and the spacing between these bars I want it 150 mm, so 0.15. And suppose the dia of bar I am selecting as P16. Okay, and I am going to apply this reinforcement to part 2. So part 2 is my slab and part 1 is my girder. So I am selecting as part 2. Okay, so this is at the top of my deck slab at cover of 60 mm. Similarly, again I will define same. This time I will keep the reference as 0.19. So basically, this is at the bottom of my slab with the cover of 0.6. So 0.06, 60 mm. So if you add basically, so depth, total depth is, depth of my section is 0.25, depth of my slab is 0.25. So 0.25 minus the cover, which is 0.06, so it will be 0.19, which I have entered here. Spacing will be 0.15. Again, the dia I will select as 16, and this will be applied to part 2. Okay, so now the turn is for my girder. So I need to give reinforcement to my girder. So for that, I will select the reference as bottom. Okay, and again from bottom the cover is 60 mm. So I will give 60 mm cover. Numbers I will keep it at 6. Spacing I will keep it at 0.15, and bar dia I will keep it at P20. Okay, so this time I will select part 1 as I want to apply this to my girder. Okay, so once I have inputted these reinforcements, I will just press OK. Okay, so now you can see this reinforcement has been defined for the section. Okay, this is at the bottom, the 6 bars which I defined, and these are the 20 bars at top of slab and bottom of slab with cover of 0.06. Okay, similarly you can define the other reinforcement as well as the face of your eye girder and the tops for eye girder. As of now we are defining only this reinforcement. Okay, similarly just press apply once, so this reinforcement will be applied to my girder. Okay, so now this was the longitudinal reinforcement which we have defined here. Similarly, I need to define shear reinforcement for my girder. So for that I will select this shear reinforcement tab. I will click on the diagonal reinforcement and I want to provide same reinforcement at I end and J end of my member. So the pitch of the reinforcement, that means the spacing of the reinforcement, I keep it as 150 mm. And the angle of my stirrup is 90 degree, those are vertical stirrups. And the area of the stirrup, so basically it is suppose a 12 dia bar, 2 leg stirrup of 12 dia bars. So I will just give that value. So this is the diagonal reinforcement which I have provided. Okay, similarly we can define torsional reinforcement as well. Okay, for now this much is sufficient for us, so I'll just press apply and close. So now we have defined the reinforcement. Now coming to the construction stages. So basically how my construction is going to happen is, first I'm going to create my substructure, and then what I'm going to do is I'm going to place my girders at the location and I'm going to pre-stress them. Once I have pre-stressed them, then after that I'm going to cast my deck. Okay, once I have cast my deck, and then my bridge will be, composite action will occur, and then it will be other utilities and all those things are going to be applied. Okay, so here if you see my construction stages here, so my substructure is going to be activated, then after that my girders and diaphragms are going to be activated, and third stage my wet concrete is going to be poured on my girders, and in second part stage my girders are composite action is going to take place. Okay, once the composite action has happened, after that post-composite stage loads are going to be activated, such as the utilities, such as the bearing surface and the crash barrier load are going to be applied. Okay, and I have made there is this long-term effect load case. So basically this load case we have defined to see the long-term effects of material creep and shrinkage on my bridge. Okay, so once I have defined all these things, I will just save this file. Okay, I will just give it a name, PSCI Girder. So what the purpose of saving this is, once we have saved this file, so we can directly open this file at any point of time, and we don't need to enter all these parameters again. So by using that wizard file, we can generate the model at any point of time. Okay, so once I have saved this PSCI Girder new file. Okay, so once I have done all these things, I just need to press OK. Okay, so now with this, you can see the substructure has, the whole structure has been generated here for us. So you can see these are the two spans and this is my substructure. So I'll just switch off the nodes so that it is clear. So you can see that this is my geometry. So these are the two spans and you can see the skew. You can see the skew of my bridge. So for better view, so this is the skew of my bridge which has been done, which has been created. Okay. So I'll just rotate. So these are the 5 girders which are been created. So now let's see the construction stages which have been formed. So you can see this is a 30-degree skew for my bridge. Okay. So now coming, so for in stage 1, so you can see in stage 1 only the substructure has been created. Coming to stage 2, so you can see in stage 2 the girders has been casted with the diaphragms are placed at the location and pre-stressed as well. So in stage 3-1, so in this stage basically the dead load of wet concrete has been applied. I will just display that. Sorry, so this is the dead load of the wet concrete which is applied on the girders. Okay, and then coming to my next stage. So in this stage, the dead load has been of wet concrete has been deactivated and my slab has been activated now. So you can see the slab has been activated in this skew bridge. Then in the 4th stage, so basically in this stage, the utilities, crash barrier loads, which has been applied at the edge of my structure. So this is the location where crash barrier is going to be cast. So that there they have been applied. Similarly, the wearing surface load. So this is supposed to be applied uniformly on all the girders. So this is the wearing surface load which has been applied. Okay, and the stage 5 is my long-term load. Long-term load case, basically to capture the effect of creep and shrinkage on my bridge. Okay, so if you see this construction stage definition, I'll just give you a brief introduction of construction stage definition. So you can see here, so in stage 1, my substructure and coping has been activated. Then the substructure boundary conditions are activated here, as well as the dead load of my structure has been activated. Coming to stage 2, the tendon, coming to stage 2, my girders and diaphragms are activated and the girder rigid links and all the support system of my girders have been activated. And with that, the pre-stressing load in my girders has also been activated in stage 2. So in stage 3, part 1, so in this stage, the wet concrete has been poured on my girders. So you can see the wet concrete load has come here, DC2 load. Okay. In stage 3-2, the same load has been deactivated and the my beams, my deck slab has been activated. Okay. So this is how the construction stage has been formed for my bridges. So there is one more thing which I want to show you before we move on to the application of moving load. What I want to show you is the construction stage for composite sections. So composite section for construction stages. So basically what I have activated here is my girder. So I need to specify, the construction stages for my composite section as well. So as I told you, my girders are activated in stage 2. So this is my girder. So these are the elements to which this girder is assigned. So you can see these elements are selected on the screen. Okay. So here you can see this age. So age of the girder at activation. So basically I want to change this age to 28 days. So what does this mean is, At the point when I launched my girders on the span, actually I placed my girders in this on the substructure. So the age of my concrete was 28 days. Okay. Similarly, so my deck slab was activated in age at the stage 3-2. As you have seen in construction stages, stage 3-1, the concrete was poured, and the at stage 3-2, my deck was activated. Basically, the composite action was happening in stage 3-2. Okay, so here also I want the age of my I want the activation of my deck slab at age of 14. Okay, so you can see the properties of my section properties. So this is individual section property for my girder. Okay, these are the stiffness scale factors, and this is the composite. So this and the earlier property will be same. So this is the stiffness of my girder, slab, and these are the composite section properties. And this H, what you see here, is the notional size of the member. So if you remember, we discussed notional size earlier by defining the creep shrinkage time dependent properties for my section. Okay, so the same, so here basically I need to update this H, the notional size based on the section dimensions of my section. Okay, so I will just press OK here. Sorry, this all the operations can be done in base stage only. I will just go to base stage. Will again modify my section here. So this I want to be at the age of 28 days, the age of 14 days. Okay, so I want to update all the notional size of the members here. I will just press update. So the notional size has been successfully completed. Now if I press this, so now you can see the notional size has been updated to 0.26 and 0.23 as per the section dimensions of slab and girder. Okay, so this is how the modeling can be done using the Prestressed composite bridge wizard. So you can see how easily this model has been generated. Okay, so now what we are going to do is we are going to quickly move to moving load application. So I will just open my presentation again. Okay, so now we have done the modeling. So now we are going to apply moving load on my superstructure. So basically what we have to do here is, so as per Astro LRFD, you all may be knowing that number of lanes if I want to find out. For that, what I need to do is divide the whole carriageway width by 12 feet or 3.6 meters. So the integer part of it will be the number of lanes, and for design lane, the lane width we are going to take it as 10 feet, which is 3 meters. Okay, so in our case, the total carriageway width is 14 meters. So once if I divide it by 3.6, I get the integer part as 3. So for our case, the number of lanes will be 3. Now coming to the vehicles, for which we need in Astro LRFD. So as you know, there is HL93 truck load plus there is HL93 tandem load. So you can see here, this is the truck load with the 8K, 32K, 32K spacing as specified in the image. Sorry. And the tandem is nothing but your pair of 25 k's axle spaced at 4 feet apart, and this is my lane loading. Okay, and there is this fatigue load as well. Only one truck is applied to the bridge without combining it with a design lane load. Now for Astro LRFD dynamic load allowance, So basically to account the effect of speed, vibration, momentum of truck live load, we need to apply dynamic load allowance. So for design moments and shear force, we need to give dynamic allowance of 33%. And if you're doing a fatigue analysis, for that we need to give a dynamic load allowance of 15%. Okay, so now we will just move to the model and we will define the moving load. Okay, so I will just switch off the hidden view so that it will be easier for us, and I will undisplay this load. Okay, so I will just activate only superstructure for the application of moving load. Okay, so this is my superstructure. I will go to the top view. So for defining moving loads, I need to go to load, to go to moving load. So for definition of moving load, what we need to do is we need to define first the traffic line lane we need to define, and then we need to define the vehicle, and then we need to define the moving load cases. Okay, so for defining the traffic line lane, so this is the procedure. It's a three-step procedure. First we need to define traffic line lanes. So here we have modeled our bridge as beam elements. Suppose we have modeled the deck as plate elements. So in that case, we need to go for traffic surface lanes. Okay, but now we are defined as line elements, so we need to define traffic line lanes. So for definition of traffic line lanes, I will just click on it. So you can see this. Just press add. So I will give it a name as lane 1. Okay. So so coming to the eccentricity, as we have discussed earlier, lane width will be 3 meters as compared to 3.6, which we considered for calculation of number of lanes. So eccentricity, this I have calculated for our bridge. So for first lane it will be minus 3.5 meters. So this is how the representation works. So from this end, so for my reference line will be this line. So I am going to apply my moving load with the reference of this line. So for that I am keeping minus 3.5 as eccentricity. Wheel spacing will be as per the code 1.8288. Okay. So now vehicle distribution, vehicle load distribution. So before that, what we need to do, we need to create a cross beam group. So basically, I will just tell you the purpose of why I am defining this. So basically these are my cross beams. Okay, so for that I will just make a new group. Okay, just add. Okay, then I will just assign these cross beams to my cross beam group. Okay, so now you can see these nodes and elements are assigned to cross beam. Sorry. So again, I will go to traffic line lane definition. Okay, lane 1. Now I will give this as minus 3.5. Wheel spacing is, so now vehicle load distribution. So as you would have attended, if you have attended the earlier webinar of this series, in that case we had gone for box girder, curved box girder bridge. So in that case the box girder was modeled as a single line element. So in that case we need to go for lane element distribution. But here there are 5 girders, 5 main girders are there. And if I am going to apply it with a reference of a single girder, and if I select the vehicle load distribution as lane element, so whatever load I am applying, that will be applied to the reference element only. It will not be distributed to the other girders. So for that, what I need to do is I need to distribute it using cross beams so that it will be distributed based on the stiffnesses of all the girders and the spacing from the load. For that, I need to select my cross beam group. I will just select cross beams. Okay, and then there is this skew angle. So basically, our bridge is in a skew. Okay, so you can see here at the start also there is 30 degrees skew, at end also that is 30 degrees skew. So I just need to specify my start and end skew, minus 30 and minus 30. Okay, and the moving direction of vehicle, I will keep it as both. Okay, so now I will just display the nodes here. So now I need to define my lane using the 2 points. Okay. One more thing here. Ours is a simply supported bridge, so we will not have negative moment at the support. But if we have a negative moment at the support, so for that we need to define lane support negative moment case as well. So for that we need to specify where is the start and end of my span. Okay. So for in this case we don't have we have a simply supported structure, so we will not have a lane support negative moment. But for in case if we have that, we need to specify the start of each span. So for suppose in this case the first this 324 element is the start of my span. Similarly, somewhere around here, so this will be the start of my another span. So that I need to specify here. But for us, it is not the case, so no need for that. So this is my lane 1. So you can see this is how my lane 1 is created at a spacing of 3.5 meters from this edge beam and the width of 3 meters. So this is the 3 meter lane width. Similarly, I will create lane 2. Okay, for this eccentricity is minus 8. Okay, cross beam. Again, I will select the first and last reference. Okay, so this is how my lane 2 has been created. Similarly, I will create lane 3. For this, eccentricity will be minus 12.5. Okay, cross beam. I'll select okay, so now you can see the 3 lanes are created for my bridge based on the skew. These lanes are created. So now I need to define the vehicle. For definition of vehicle, I will go to add standard. So dynamic load allowance, as you know, we need to take it at 33%. Just press OK. Okay, so now I will define the moving load case for this bridge. Just name it as moving load case 1. Okay, I will select the combined effect of all the things. Just press add. Minimum loaded lane, I will keep it as 1. Maximum loaded lane as 3. I will select all the 3 lanes. Press OK. Press OK. So moving load case has been defined here for me. Okay, so this is how we will define the moving load for our bridge. So now we have defined all, so I will just summarize what we have done till now. So first we have defined the material properties, and post that what we have done, we have defined the time dependent material properties. Then we have defined sections. Then we have done the geometric modeling using our wizard, uh, using pre-stressed composite bridge wizard. Then post that what we have done is we have defined the moving load as per Astro LRFD. Okay, so once we have done all these things, so now what we need to do is we need to run the analysis and see the results. Okay, I will just run the analysis. So we didn't add any lane support negative moment in this case, but if we would have had, so for that, just we need to define the lane support negative moment for that case. Okay, I think it was covered in the previous webinar. If you have any doubt related to that, I will send you a material. Just let me know if you need anything related to that. Okay, so the analysis has finished. So you can see how quickly the analysis is done. So it is done in about a 1 minute, 61.88 seconds. So once the analysis is done, what I will do, I will make load combinations for my bridge. So for load combination, I will go to concrete design. We have this auto generation option. Okay, so suppose I want to make load combinations as per Astro LRFD 16. So I just need to select concrete, my code, and I just need to press OK. So based on that, the software will automatically create the load combinations. Okay. So once these load combinations are made, we can go to the results. Okay. So suppose first let's see the results for bending moment shear force diagrams. So suppose for stage 2 when only girders were casted, so in this case, suppose dead load. So I will activate only the girders as I am only interested in my girders. So you can see here, this is my girder diagram. So the bending moment due to dead load in my girders is around 1374 kilonewton meter. Okay. Similarly, tendon primary force in my girder, if you want to see. So this is the tendon primary moment which is coming in my girders due to pre-stressing. So if you remember, my girder by tendon profile was in curved shape. So in similar way, tendon primary profile also I am getting in the similar way. Okay. In the similar case, we can see for dead load, if you want to see shear force diagram. So this is the standard shear force diagram. Similarly, post. So once my slab has come, so I will just activate my superstructure. So this is how the bending moment shear force diagram is for my substructure. Okay, so now coming to post shears, let's see for moving load. So for moving load 1, maximum, where I am getting the maximum moving load, I am getting it maximum at member number 84. So let's see where member number 84 is. So this is the member where I am getting maximum bending moment due to moving load case. So what if I want to see the vehicle position due to which I am getting this maximum bending moment here. So to see that, we need to go to moving load tracer. Okay, so I will go to beam force and moment. So my member number is 84 for MY. Okay, and just see the vehicle position. So yeah, so you can see when it is a single lane loaded. So this is my lane 3 which I have defined. So single lane which is loaded here. For that I am getting the maximum moment at member number 84. So now we have one more option here. We can convert this moving load, this vehicle position into a static load. To convert that, we have this right maximum load option. So suppose if you want to add centrifugal braking force as well, you can do that. Or else in moving load only vertical load has been considered. So if I press that, this MCT file will be generated. Just control, I need to copy this and I need to paste it in the MCT command shell. So my analysis will be deleted for this. So once I do that, you can see a new load case has been generated here. Static load case 6 MB max MLC for 84 member MY. If I display this, so you can see the vehicle load position for which you are getting maximum bending moment at 84 member. Okay, so this is how we can see the results, concerned results for our bridge. Similarly, if you want to see the results in the tabular format, all those things can be seen here in result table. If you go to beam, we can select force, stress and all those things. And if you want to see the stresses in for composite section, part-wise stresses, part-wise forces, so that we can see is composite section for construction stages. We can see the part-wise stresses in my slab and my girders. Okay. So once the analysis is complete, we will see how we can do the design of my PSC girder in MIDAS civil. Our time is already we have already exceeded our time. So I will just take 5 more minutes. We will see the design. We will see the design of superstructure and substructure. And then if we have any questions, then I will attend to that. Okay. So to see the, I will just undisplay this load. So now for design of PSC, what we need to do, first we need to select the code according to which I want to do the design. Suppose I want to do it as per Astro LRFT 16. Okay. So here first I need to specify the basic parameters, what output I want, and what kind of tendon we have, what kind of corrosive condition, flexural strength, construction type we need to specify. Okay, so for now I will select all the output parameters here, and I will keep the standard input parameters and press OK. Okay, so now I need to define, so earlier if you remember we defined these materials. But for these materials, we have not given any rebar data. So for that, I will just give the rebar data. Suppose grade 50 steel we are using. Similarly, for slab was grade C4000. We'll select same rebar grade here. Okay. So once I have selected it, I need to modify my material. So my material has been modified here. Once I have modified my PSC material, so I need to define the position where I want my output. So suppose we have seen the result for 84 members. Suppose I want to design member number 84 itself. So I will just select member 84, apply. Similarly, I want output also at that location. So I will again select 84 and I will again apply. So the input and output position I have specified is for member number 84. Okay. So similarly, service limit, this load combinations, as I have generated automatically auto generation option. So these load cases will be segregated automatically. So coming to interface shear, so I will select the Girder elements. So suppose I need to apply what type of interface I am providing. So if it is roughened CIP slab, or if you are providing any reinforcement or to encounter interface shear, that we can specify here. As of now, I am giving this roughened slab interface. Just apply. Okay. So once I have done that, I just need to perform the design. So you can see the design has been completed. So I'll just generate the Excel report. So it is going to take time. So I have already generated a report. So I will just show you that report. So yeah, the report is generated for our section as well. So for 84 member, we have generated the report. So you can see these are the section properties for the section. And these are the detailed calculation based on our H2 LRFT. So you can refer these clause and you can see the calculation and how the forces are coming in the section, and each shear check and all the checks are performed here. Minimum shear, torsional check. So you can go in detail and you can verify all the results. So similarly for the other section also we can. Coming to tendon stresses. So we have not seen, I have not discussed the tendon losses, how we can see them in MIDAS. So I'll just quickly show you how we can just see the tendon losses in MIDAS. For that we need to go to results. We need to go to tendon, result table tendon losses. So here, I'll just change the unit to Newton mm. So here we have seen, so you can see my pre-stressing I did in stage 2. So from there, these stresses are coming. So based on the stresses. So what you see here is stress after immediate loss A, and then there is this elastic deformation loss B. So what this stress after immediate loss A is, so if you remember, we have stressed our tendon at 1395 Newton per mm square. So now the stress is around 1248, 49, 1250. So 1395 minus 1250 is the immediate loss that has happened in the tendon. So now ours is a post tension. So for post tension, immediate losses are for immediate losses are my friction and wobble losses, ankle slip losses, So these immediate losses will be deducted, and whatever stress after immediate loss is this um, stress part A. And this stress part B is the losses due to elastic deformation of my member. So due to creep, shrinkage, and whatever change during the course of my life of my bridge. So whatever losses which are going to happen, that will be incorporated in this elastic deformation loss B. Okay. So if you see, as per the age, these loss will be changing. So this loss will remain constant as it is after immediate losses. So you can see these are the long-term losses. So this is how we can check the losses in my member, in my tendon. This can also be viewed in this tendon tension loss graph. You can just see how the stresses are changing in my tendon along its length. So the tendon force and the distance. So for any of the tendon we can check. Okay, so this is how we can do that. So now coming back to design. So now we have seen the design for my girders. Now coming to my substructure design. So for substructure, we have this RC designed section here. So based on, so ours is a solid track section. So if the section is standard rectangular or circular, that type of design can be done directly in this design tab. But for a specialized section, such as this recto-circular section, what we need to do is we have another tool called General Section Designer. We need to export this section to General Section Designer. We need to define the reinforcement there, whatever load cases for which I want to design, I need to specify, and based on that, you can perform the stress check. So I'll just quickly show you how we can do that. So just I've opened this General Section Designer here. Okay, so I will just link it to the MIDAS file, in which we are doing the modeling. Okay, so I will just select my pier section here. Okay, so I have selected the pier section. Just open the GST. So you can see this pier section element has come here. So I will just import it. So it will ask me for which load combination I want to perform the design and for which part I want to perform the design. So I will select only one part, part I. So now this is the section of my bridge. Okay, so if you see here, I will just define the reinforcement for my section. So there are again various ways to define the reinforcement. I will select perimeter option. Okay. So here again my cover I will keep it as 65 mm. I will select the dia of bar as T22, number of bar as 38. Okay, just press OK. So you can see the reinforcement has been defined here. Again, just a second. I will just save this once. Sorry for that. Okay, so here, so this was my column section. I will again just select the section. Okay, my link is not established. First, let me establish the link. Okay. Just import that. Select the load case. Sorry. Okay. Okay. So here I have my section. I will just give it a reinforcement, perimeter reinforcement. Just press OK. Sorry. So once I have defined the reinforcement, what I need to do is I need to specify the design code. So now I am doing it as per ASHTO LRFT 12. Okay. Then what I need to do is I need to check the section properties. So section properties I will say. So now the section properties are calculated for my section. I have defined the reinforcement. I have defined the load cases for which I want to do the analysis. Now what I want to do is I just need to design my section. I will just save it as section 2. So now it will just perform the design for my section. Okay, so now you can see here, these are the PM interaction curve drawn for my section. Okay, then this is the MY-MZ interaction of my for the pier, and this is the 3D PM interaction curve for the pier. Coming to the stress contour, so now this is the elastic analysis crack status for my. So this is the this is my CG. Sorry, this is my neutral axis for my section. If I see for the cracked elastic, so this is the cracked elastic stage. So this is the neutral axis for that section. If I see for ultimate state, so this is the unit in kilonewton per meter square. So if I want to see the, so this is my strain profile along my section, and these are the stress block parameters for the section. So these all things we can see here in the GSD section, and I can get this in the report format as well. So my report is generated. So this is the report which is generated for that stress block and strain parameters. So these are the forces and stresses in each bar. Okay. So this is how we can use the design options in MIDAS Civil. So this is how we can perform. So we'll just close this. So now what we have seen, I will just summarize everything. So from starting, we have seen how we can create material properties, section properties, then how we can create the geometry with skew, with curvature in PSC wizard, PSC composite wizard. Then how we can apply moving load using MIDAS civil for Astro LRFD case, and then how we can perform the design. Okay, so now it is already 30 minutes past the specified time. So I see there are a few questions. So there are a few questions. So what I will do, I will just reply them on via email. So as it has already passed the time, so I will just reply all these. I will write all the questions and I will just reply them in an email, and I will share it with everyone, so that it will be helpful for everyone. So thank you for joining this webinar. Thank you for having patience and listening to me for this 1.5 hours. I hope it was useful for you. And yeah, if you have any further questions, so just mention them in the comments tab, so that I will compile all the questions and I will reply them to you via email. And further, if you have any other questions, so what you can do is we have this global support.midasuser.com. So you can post your queries here as well. So we will resolve your queries through we can resolve your queries from here as well. Okay. So thank you all for attending. Hope to see you soon. So I'll be ending this webinar now.